Welcome to our second lecture of Cook the Science. I think it's really amazing to see so many of you. This time we got even a bigger room and still we could fill it. So that means there is a lot of interest in this topic. I'm a foodie myself, and so I think it's a really nice topic, but it's really nice to see how many people are actually interested in this. So I'm Thomas Michaels. I'm a professor of soft and living matter physics here at ETH. I'm part of the Department of Biology and the Bringing Materials to Life consortium. And for me, this Cook the Science lecture is a way to popularize this amazing field of soft matter. So to raise awareness that there is also a branch of physics which deals with things that we see in the kitchen that is super fascinating. For me, I use soft matter in the context of biology, but it's really, in cooking that we see a lot of these soft matter phenomena come alive and become part of our daily life. And so it's something that really connects science with the public. And so that's a little bit the idea behind Cook the Science. So it's inspired by the Harvard Science and Cooking lecture, which I attended when I was a postdoc at Harvard. And so every evening we have a different soft matter topic. And then we look at this topic also from the lens of chefs and bakers tonight to see also how these topics apply in a practical setting. And so the topic tonight is elasticity in the context of bread making. And to illustrate this, we have tonight a wonderful guest, Jens Jung. We are really honored to have you here. So I guess you probably know him in Zurich. He's really one of the most famous bakers in Zurich, owner of John Baker and Jung Bakeries. Thank you for being here tonight.
Thank you. Back, Thomas.
But before we start making bread, I am afraid you have to endure some science. So I will be the boring scientist telling you all the science behind it. You can escape now. This is the last chance. And then we will go into more of the bread making. And so what I find really interesting or fascinating when I think about bread is that if you think about it, we are working with just 4 ingredients: flour, water, salt, and yeast. Sometimes we make also enriched bread, so we can add fats, we can add eggs and things like that. But in the simplest setting, we have only these 4 ingredients. And yet, we are able to combine these 4 ingredients to make such an amazing array of different types of bread. And the proportions of these different ingredients control every aspect of the bread: the crumb, the crust, the texture, the color, the taste. And so it becomes really interesting to see how you combine these ingredients to give rise to the different properties. And so here, precision is key, because if you mess up by the ingredients, you don't use the right amount, you don't use the right temperature, everything doesn't work. And this is somehow why people who like to cook often say that they can't bake. It's really because everything is so precise. And tonight we want to understand why is it that things have to be so precise, and what are the physical phenomena behind this. So from the soft matter perspective, the topic that I would like to discuss tonight is what is called viscoelasticity. So viscoelasticity comes from 2 words, elasticity and viscosity. So viscosity is a property of fluids that flow, whereas elasticity is a property of solids when you deform them. And viscoelastic materials, such as, for example, bread dough, lie somewhere in between. So they are a little bit elastic, they are a little bit liquid, so they combine this viscous and elastic behavior. So how can this be? Well, to understand this, let's start to look a little bit at the basics of both elasticity and viscosity. And let's start with elasticity. So elasticity, excellent. So the idea is that we clap when we see an equation. So I haven't announced the equation yet, so when I'm going to name the equation, then you can clap again. So the idea is that So if you take a solid and you apply a small deformation, the solid effectively behaves like a spring. Okay, so you apply a force, it deforms, you remove the force, it goes back to its original position. And this can be described by Hooke's law, which is this equation over here. So that's the first equation of the evening. And this equation relates the stress, which is the force applied per unit area, to the strain, which is the relative deformation of the material, so the percentage by which we deform the material. And the proportionality constant is this elastic modulus E here, which is a material's property. So it describes how hard or soft this material is. So a material like, for example, diamond is very hard, so it has a very strong elastic modulus and deforms very little, whereas a soft material like, for example, rubber or dough deforms much more readily and has a much smaller elastic modulus. So this is how we think about elasticity in the simplest setting in physics. And but how can we think about this elastic modulus? So the units of elastic modulus are pressure. So the elastic modulus is measured in pressure units. And pressure is a force divided by an area, which can actually be rewritten as an energy per volume. And this is actually really interesting because, yes, please. This is very interesting because what does it mean? It means that effectively this elastic modulus, which, as I said, describes the elastic properties of the material, and it's a material's property, somehow describes the energy density in the material. And so that's our next equation of the evening. So the elastic modulus is the energy per unit volume in the system. So you can think a little bit as an elastic material, as a material made of different components here that, for example, molecules which are connected by springs that represent the bonds. So these springs have a characteristic length scale L and have a characteristic energy scale U. And so what the elastic modulus tells us about is pretty much how many of these springs we have per unit volume. And so this somehow, it's very interesting because we now start to understand why certain materials are hard, whereas other materials are soft. It really has to do with the different energy content in the material. And it has to do with the building blocks. So if you're thinking about a hard material, like, for example, diamond, the building blocks, so the components are atoms, which are very small, and they also interact very strongly with each other, relatively strongly. Whereas, and this results in a high energy density, so a high elastic modulus. Whereas when you're thinking about soft materials, for example, bread dough, then the components, the constituents are much larger molecules. So they are proteins, starches, which are huge molecules and also interact much more weakly. And so that means that our springs are much larger and they're also weaker, and so that results in a lower energy density. And if you see here in this equation, you see the energy divided by the length cubed. And when you cube a number, when you do to the power of 3, it becomes huge very quickly. And so that means that the length scale is actually the dominant factor here. So really, the reason why a material like bread dough is soft and deforms so readily, it's really because the constituent molecules are these macromolecules, which are large, proteins, starches, lipids, and so on, which are common to many foods. Now, where does elasticity in bread come from? Well, elasticity in bread comes from the flour. And the flour, of course, is like the structure of the bread. And in particular, among its constituents, it contains two proteins, glutenin and gliadin, that form an elastic network, what we call gluten, when in the presence of water. So these are these two types of proteins, and in the presence of water, these proteins interact. The glutenin form these like long strands of molecules, which are then connected to form this elastic network, which is almost like a mesh, if you want, and that gives elasticity. And this happens in and you can see now also where the elasticity comes from. It is again associated with the length scale of this elastic mesh. And now you understand also why flour itself is not elastic, but dough becomes elastic when you add water. It's really because you need water for this transformation to occur. So this was elasticity. The other element in viscoelasticity, as I said, is viscosity. So viscosity is the resistance to flow. So it comes from Newton's law of viscoelasticity. Thank you. Which is this equation over here. And by the way, just in case you were wondering, this is not the same as the Newton's law of gravitation. So Newton did also some work in the context of fluids. And so we have also this Newton's law of viscosity, which is perhaps less well known. And what this equation tells us is that if you apply a force to a fluid, the response is very different. As we've seen, if you apply a force to a solid, the solid deforms by a certain amount, and then you remove the force, and the solid goes back, or the elastic solid goes back to its original position. Whereas if you apply a force to a fluid, the fluid flows. Okay, so it's a very different type of behavior, and it flows faster the lower the viscosity. So the viscosity here is this parameter here that links the deformation, so the applied force, and the flow of the material. And at the molecular level, we can think of this viscosity effectively as a kind of friction between the molecules and as they flow over each other. And here are typical values of viscosity. So viscosity is measured in Pascal times second. So here actually millipascal times second. So water has a viscosity of 1. Olive oil has a bit higher viscosity. Honey is way more viscous, as you can say. And also dough has actually a viscosity. I mean, it's actually really high. But if you think about it, dough is not only elastic, but it's also fluid. So it flows. If you leave it on the bench, eventually it will flow. It's just that it flows so slowly. It takes such a long time for it to flow. And this is reflected in this very high viscosity. Now, what is very interesting or important to note here is that the units of viscosity are Pascal times second. So it's a pressure times a time scale. And so this is very important because it tells us that there is a time scale here. And this is a crucial element. Why is this? Well, because if you're now thinking about a viscoelastic material that combines this liquid and or viscous and elastic components, whether the material behaves like a viscous fluid or a solid depends on time. And this is the next equation of the evening here, that effectively that the ratio of the viscosity to the elastic modulus is associated with a time scale. And so this time scale is effectively the time scale that separates the times at which the dough behaves elastically or viscous. So this equation here tells us that you look at short times, the dough behaves elastically and behaves like a solid. So if you punch it very fast, it responds elastically, but over longer time scales, the dough has time, or the elements in the dough have time to relax, and that actually causes the dough to flow. And so really this time scale here, tau, is associated with the relaxation time scale. Now, of course, dough flows, but bread doesn't flow. So if you don't want the dough or the bread to flow, what you do is effectively you want to set this dough into place so that it doesn't flow anymore, and you do this in the crumb when you bake bread. So in the crumb, the proteins are dense, and also the starch is gel, and this effectively sets the material, not allowing it to relax anymore. And but now, before moving on, I want actually to show a little experiment here. I have a material, well, actually here is just cornstarch and water. So I think it's an experiment that many of you maybe have seen already. And this is to demonstrate really this property of some materials to respond elastically or in a liquid-like manner, depending on the time scale at which we look. So again, this is just water and starch. I hope it works. But what you see, I need maybe to move it a little bit, but what you see is that when I go very slowly, I can actually put the spoon into the material, so it actually behaves like a liquid. But if I do very fast, it actually behaves like a solid. So I actually cannot go through the material. And so really this depends on the time scale at which you are looking at the material. There are a lot of these materials, as I said, are super interesting, and there are a lot of them. And I urge you to think about how many we have in the kitchen and to play with them. There are a lot of interesting phenomena also that occur with these materials. And one of them is the Weissenberg effect, which maybe you have seen when you make dough and you knead it with the machine. And the Weissenberg effect is the following. So if you take like something like this, a rod, and you turn it into water, you will create a dip. But if you do this in some viscoelastic materials, what happens is that the liquid climbs. Okay, and so this behavior comes effectively from the elastic nature of the material. And so you don't see this with simple liquids, so you really have to go to these complex liquids or viscoelastic materials to see this type of behavior. And so now let me go back to the slides. As I said, just very briefly, the next equation here is the Weissenberg effect, which, again, it's a property of some viscoelastic materials, and it's, here the equation describes the so-called Weissenberg number, which, if you want, is like a ratio between elastic forces and viscous forces, and in a pure liquid, we don't have these elastic forces, so this term here is 0, but in some viscoelastic materials, these terms here can become important and give rise to this Weissenberg effect. So now, before we start making bread, I thought that I should summarize a little bit the stages of bread making. And so what is a little bit very roughly and like in a simplified manner to give you a flavor of what are the different things that occur when we make bread. And so the first step is when we make dough. And so the first thing that we do is we mix flour and water, and as we have seen, this creates this elastic gluten network. Then flour also contains starch, and starch is contained in these starch granules, which are, if you want, little containers that contain starch molecules. And these starch molecules are called amylose and amylopectin, and they are long chains of glucose molecules. So you see this building block here, the glucose, it's really copied in many copies here, and it forms this long chain. And this is the sugars on which the yeast feeds on. And so when we make dough, we also have yeast that, as I said, eats the sugar. And when the yeast eats the sugar, it burps and farts and does all these kind of things and releases carbon dioxide as a result of this. And this carbon dioxide is responsible for the bubbles that we really like in bread. In the presence of oxygen, it does this through aerobic fermentation, so where effectively you take these sugars and then it produces CO2 and water. And as oxygen runs out, we switch to anaerobic fermentation, where you produce CO2 and ethanol and other compounds that give really some of the aromas in the bread. But what is most important is that it forms these bubbles, these gas bubbles, and here the gluten network is very important because it traps the gas bubble like fish in a net, if you want, and without this elastic mesh, the bubbles would simply disappear. So it's really important that we have this elastic mesh. Now, the last part is, of course, now we start to bake the bread. So what happens when we bake bread? Well, the first thing that happens is we have the so-called oven spring. And so here, when you heat bread, yeast accelerates fermentation, so yeast likes heat. So the production of CO2 increases, but at some point the yeast starts to die. The ethanol produced by the yeast evaporates, the water boils and forms vapor that further inflates the bread, and also CO2 expands. So these bubbles expand, and this is what we know from basic physics. And here is the next equation of the evening. So the ideal gas equation, which is the ideal gas equation, which is the simplest framework we have to rationalize why gases expand at higher temperature. And so this really, all these effects together create this last lift in volume and expansion as we put the bread in the oven. And then, of course, we have the formation of the crumbs. So this is really, if you want, the cooking of the bread. And if you want, from a soft matter physics, what the bread is a set foam. So it is set into place because as we increase temperature, the proteins harden and also the starch starts to gelatinize. And so they form this gel and this more solid structure, if you want, that sets the bread into shape and the bubbles that have formed in the meantime. And the last point, of course, is on the crust. And so at the surface of the bread, the water evaporates. And as the water has evaporated, we can reach temperatures higher than 100 degrees. And that allows us to start some of the browning reactions that we have seen in the last lecture. You may recall the Maillard reactions and caramelization with the remaining sugars, which give this brown and crispy crust, and also are responsible for the aromas that we see, that we like in the crumb. And so finally, here, how can we think about this crust formation? So here are simulations of formation of the bread baking. And so here you see the temperature in the bread dough as the time increases. And so what you see here is a cut through, so at different times, different positions in the bread, and you see how the temperature increases until it reaches this 100 degrees, which of course is a magic number because that's when water boils. And so until you have boiled all the water, the temperature stays to 100 degrees. And so the water evaporates much more faster as the surface, so the temperature goes to 100 degrees, but then rapidly starts to increase, whereas in the core, the temperature stays to 100 degrees for much longer because it takes longer to evaporate. And so what we see here at the surface, then we can reach these temperatures of 130 degrees for the Maillard reactions to start, and also as we increase the temperature further to 160 degrees, we start to get this caramelization. And so I've spoken enough. This is all I wanted to say, to give you a little bit of an overview of how a physicist, humble physicist, thinks about bread. And I got hungry, I would have to admit, as I thought about bread. So I think it's time to start making some bread, finally. And as I said, I'm really delighted to welcome Jens Jung with us tonight. And I'm really looking forward to learning more about bread.
Welcome everybody. Thank you so much for coming. It's a big auditorium. I'm quite nervous. I want to thank you to ETH and Thomas for having me as a guest here. It's a big honor to speak here in front of you. And thank Susan and Remo for introducing and making this also possible from Taste Lab. Thank you, Cynthia, and my 3 fast-growing kids. Thanks to my dad, who opened the bakery when I was 5 years old. That's where I know it from, that it's not easy. And he is probably why we are here now today in many ways. The story begins. I'm excited to talk a bit about myself, talk about John Baker, the Jung Bakery, and show you some interesting facts, stories about elasticity and bread making. 11 years ago, I quit working at my dad's bakery. And the journey since then, it feels incredible, it feels fantastic. I followed my passion, and when I quit the job, I missed this these emotional moments that when you sell bread in your store, it's always kind of a very special moment. In the morning, many people come into the bakery, and this first words they speak is like, I want to have a croissant or a cappuccino or something. So you have this nice connection after you have worked at night and see the bread come out of the oven. We gathered up, we are 4 founders of John Baker, and we started this bread revolution in Zurich. I got to know like the sourdough revolution in San Francisco in the end of '90s, and I was really amazed about what they do with bread and sourdough. We started with a transparent, cool, organic bakery at Stadelhofen. It was all about making the best bread in the world and having as much fun and fans as possible, and go and tell it all over the world. So we got a big attention at that time, so we got lots of people visiting us, writing about us. That was a time. We were actually, I think, at the right time, in the right moment, did the right thing. So now I'm here speaking about bread at the ETH. It's crazy. John Baker has 4 bakeries in Zurich, and we also have a wood oven bakery at Casa Caminada with Andreas Caminada since a few years. The bakery Jung just merged with the bakery Kleiner from the ZTV. So the whole group now has a big production site in Altstetten, 9 shops at Bakery Jung, and the total team now is about 250 people. So we grew quite fast, and with all its favors and ups and downs and everything. And we process more than 300 tons of flour every year. So that's more than I ever dreamed of. You know, it's kind of a lot. So my passion was always for good products and producers, also funny ones, and some special producers that don't go the normal way. They go like they always have passion in their products, and then use as few ingredients as possible and let time and nature work. That was always kind of the fundamental thing we tried to do with John Baker. I have to start my dough now because it takes a while until it's finished. So I put in the flour. This is 800 grams of flour, 640 of water. I have to concentrate. Where's the balance here? And what is nice about making dough, you can kind of make it from scratch and just watch how it develops. So if you put more water in, this is just a Polish. That's like a Ferrari sourdough, which doesn't taste so good, but it's really fast. I made it this afternoon, so it grows to double within 1 or 2 hours or 3 hours. It depends how much yeast you put in. It's easier to make that because sourdough takes 24 hours, and we don't have that much time here. I put the salt in right away because it's a small dough. Normally we put the salt in later. Salt, it's crystals, destroys the gluten strings because it's a crystal, and it has sharp edges. Have everything inside, huh? Okay. Salt, everything is in there. So what we do now is we kind of mix everything together, try to dissolve all the water, the more water as much water as possible, and it's just like it's mixing. If you wanna have it knitting, you have to give much more energy. So this first stage takes about 20 minutes. If you put more water in, it takes 30 minutes. If you put less water in, it takes 10 minutes. So you can kind of choose how fast your dough is going to be. We go for the long one because you can put more water in, so it stays longer fresh, and it just has a better, tastier, savory crumb. I just leave that running. About the flours, the flour, the grains, it's a big story because it's kind of, there's a lot of mystics and misunderstandings and urban legends about it. What's more important is where does it come from? How is the grain brought up? And how does the baker make it? How much time does he give it into the production process? And of course, how the wheat is brought up. There is these big companies that sell a seed to plant the whatever, it's like a wheat or so, and they give you, it depends where, they give you a cocktail of herbicide, fungicide, and fertilizer. And so they kind of make the world grain, and then they just adapt all the things that come from the outside. And what we do, we source locally. Our grains, they're brought up, the seeds, they're brought up in Schaffhausen or at the lake in Zurich, in Schmerikon. And that's why they are used to this climate, and they're used to this area, to all the fungus and all the illnesses and the climate. So then it goes to the mill. The miller has a really hard job in Switzerland because our climate is not perfect for the grains. The soil is not perfect. So if we would make this bread with like grains from United States, Ohio, the bread would be like, wow, even more wonderful than it is now. But I think with a good head miller, with a good miller master, he knows how to screw the mill, and that's how we choose our mill. We always look at who does the milling and who's the boss there. This is crucial. Like a good head baker, a good head miller, and a good breeder, it's really important for the whole product at the end. Because as a baker, I think you get like 10 or 20 times the perfect loaf a year. The rest of the time you think like, oh no, it's not perfect, but it's okay, you know? And you can't turn it back. So if you had your ingredients, you made it, you had your temperatures, you have your pH meter, and you have your stopwatch and everything, it just doesn't work all the time. Good. Water is baker's gold. The more water we put in, the more money stays with us. But it makes the bread taste good, have a soft and juicy crumb, and makes it last longer. The more water you put in, the longer lasts the bread. Salt, I don't know, chemically or physically, I think every salt is the same. I like sea salt. Tastes different. It is different. I don't know. I think that's a love or hate thing or a trick in your mind. The one ingredient, yeast or sourdough, I talk about that later. That's a big topic. Of course, law of time and the force of nature is very important as an ingredient. You always have to think about that. And as you said already, there's fats, sugars, eggs that we can make different products, make it very characteristics and make it sweet, make it salty, make it soft, make it big, make it hard, you can do everything. I don't go into that so much. What I'm going to do now is show you how we make the pulish. This is the fast. You can do the same thing you can do with sourdough. It just takes, instead of 1 hour, it takes 24 hours. It depends a bit the temperature you take. The cooler you go, the longer it takes, the more acidic it gets. The warmer you do it, you probably get a little bit more volume, and you get milder aromas. So there's a different thing afterwards. So what we do for the pulish, we have this water. Is this one?
Yes, that's the.
This one.
I hope it's warm enough.
Yeah.
Yeah, good.
It's 30 degrees.
He told me to get water at 30 degrees, so I went to the toilet actually to it was quite with a measuring pistol for the temperature. I went, and there were a lot of people there, so I don't know what they thought. So I think it cooled down a little bit, but we have a bit hotter water here in case you need.
It has it's a bit too cool, but I just want to show you how easy it is to make like a starter, to make like a pulish. You can make that for, if you make your Zopf, your Butterzopf, you can put it in if you make your bread, and it's just an easy and fast way to kind of get more action into the dough. Oh, this is the dark one. Doesn't matter for pulish.
So how much flour do you have there?
That's 1-to-1.
1-to-1.
Yes, it's
water and flour.
Water and flour and yeast, of course. Huh? You can play with the yeast. The faster you want to have it, the more yeast you put in there. If you want to double in 1 hour, you put about 15% of. This is fresh yeast from the Swiss Schweizer Hefe, which is a monopolist, I think. And it's really expensive too. Crazy. I don't know. That's the Swiss East Company's gold. So what you do is you kind of
Don't worry, we clean afterwards.
The mess in the ETH. I watched the lecture from John Leahy in Harvard, and it was like the whole room was full of dough. But I figured I don't do that. But what you see also is like what we do here. It takes 20 to 30 minutes. I did the same thing. I did the same amount of flour, water, and yeast, and I just mixed it together like this. And you wait, and I show you afterwards how that works. That's when we talk about Jim Leahy, about the no-knead bread. That's a bread you don't have to work. But when you look at it, in the modernist bread, they made all these samples, and there's the no-knead bread doesn't have this really beautiful big volume that you can get with this one, but it's quite a good bread.
And so how did you choose this temperature of 30 degrees for the water? After experience, or?
No, that is where the yeast has the most activity, I guess, no? 30 degrees is more or less there where the yeast works as the most. So that's what I said. It's like a fast and turbo sourdough, which is not sour actually. The pH numbers, they don't go really way down. It's goes down to 5.4, 5.5, and this is it's not sour. Okay, this was the polish. We can make a rubber, so we see how much it goes up until we're finished. I don't know how I'm in this time schedule. I have no idea. So I just talk as long as we have time, and then the rest. You have to kind of tell me if I have to speed up or. So, as I said, I made this dough earlier. This one, I just mixed it, and you have to see how it does now, without mixing, how much structure and how much like a dough it is already. See that? It is. You cannot yet have it have the really nice gluten window, but if you now go on and fold it a few times, I'm going to show you now how to fold. It has already a nice built-up gluten strings.
Network, yes.
Yeah. Happy to have a scientist here. My thing was always like, I knew how it works because I went to school about and how to do that. But at the end, it always came out right by just doing it. You know, I kind of, after a few thousand kilos dough, you get kind of the feeling how a dough, when it goes, then it's finished, and then how much you have to do. So I have to look if, yeah. What you can do, what the San Francisco guys do, they make an autolyse. That's when you put a part of the water with the whole flour together, and you wait. You can wait 2 hours. You can wait 20 hours, and then put all of that into the dough and mix it. Go on mixing. You can get more water into the dough like that. That's what we bakers try to do. We try to put water in it, and then we sell the air in the bread. That's the way it works. That's the way you get like That's my equation. So, kneading, it's still mixing, you see. We still have 3 minutes to go. It's already 17 minutes mixing. Afterwards, we're kneading. And what you can do if you want to make the strings even longer, and if you want to give it another punch, another movement, you can fold your dough after about 1 hour, or the shortest is about 20 minutes. You kind of fold it together, and you can see that the dough has this energy again. It sits there again and is kind of punchy, you know?
Yes.
And as you see here, when you don't do that, it just goes relax, and it's like a couch potato.
So, quick question, if you paid attention, what is the name for this type of behavior? Elastic, viscous, different time scales? Can someone answer? There is a prize, actually, if you answer right. Yes? Very good. Perfect. So you win 1 bag of flour.
Can I ask a question?
Yeah.
Because you said that ethanol evaporates at 87 degrees.
78, yes.
Yeah. And so if you eat bread at 77 degrees, you can get it.
Well, the point is that actually, when the bread comes out of the oven, actually the internal temperature is higher than that. So it's actually closer to 100 degrees, 95, 100 degrees. So really the ethanol has evaporated then. So I think you better soak the bread in alcohol, like
If you want to.
like they do, for example, in Naples, right, with the baba, room baba, right? So they bake this thing and then they put it in the room and sugar, and it's kind of delicious.
Yeah, it is. I never thought of that, but I think when you don't get the temperature, it's just not. You can eat. It's like eating dough at the end.
Yes.
If you don't get over, I think from 60 degrees, the starch
Yes.
begin to.
But if it is not properly cooked inside, then the dough actually collapses, right? Because effectively you don't have really this structure from the gelatinization, and so that kind of holds the thing together. So you would have actually some crumb outside, and then you would have the uncooked dough in the middle that just comes out. There is a beautiful picture on that in the modernist bread, actually, of uncooked or undercooked bread. So, but it's a matter of taste in the end. So.
So here the dough is already okay. I put another.
By the way, how do you see when it is done? Because you said 20 minutes, but then also it can be 30 minutes or 10 minutes, depending on,
No,
so
now
how do you see it?
No, now it already has kind of those strings, but it's not it's without energy. It's like just mixed very well. I could go on with this for another 10 minutes and then have almost no kneading time. Mm-hmm. But you can start as soon as you see that it's not a soup anymore, so it's becoming kind of a dough, kind of a soupy dough. You can start with kneading. Kneading is giving the energy into the dough, and also heating it up a bit. It's kind of it's a process where the friction also gets the temperature to rise. 23, we should be at 25 at the end. Okay. More about that. Relax. Fold it to get the tension back. Let it relax. Fold it, and you get a really beautiful bread. We try to keep the dough. As I think I said it earlier. The warmer it is, it gives it a milder taste. So if you're like in the range of 25 to 24 to 29 degrees Celsius, you get a more bubbly, but less acidic bread. And if you go down to 18 to 21 degrees, you get those acids are produced a lot more, and you get more compounds of aroma compounds. So what you try to do is not to get too acidic, especially in Switzerland. When you say, "Oh, we have sourdough bread," "Oh no, I don't like sour." But as we do it, we try to keep it on a sweet side in the way that we take the dough earlier before it gets sour, before the pH level goes down too much. So now you see, it says hello. You can actually hear it now. It's not the clapping on the wall, it's like the bubbles that get crushed inside the dough. Let's see if it's finished, huh? Can take a little dough, and I always do it with water. It's easy to do the sticky dough and see how it is a big, nice window you can read the newspaper through. When you knead it too much, when you hold it like this, it drops like liquid. Then it goes back to a different stadium. It goes over the top, and it gets liquid again. Yeah. Yeast is a big topic. We have, since COVID especially, we have lots of knowledge about yeast, and everybody makes bread at home. And there's lots of mystics about it. Also, there's like those 1,000-year-olds or grandfathers, sourdough. There is lievita madre. There is yeast water. You shouldn't drink that. I don't have to mix that with that one, because otherwise I blow up. You can use all of them it's like the thing is, with what do you work, with what do you like to work, and how fast has it to be. The best result is still with the slowest possible way, I think, for the bread, for the volume, for the taste, for the crumb. The slowest possible way is always the desired one. But you want to have good bread, and you want to have it tomorrow. There's so many ways how you can speed up and still have like a 90% loaf on your table. So try to experiment with different kind of yeasts and different kind of way to ferment, and find your own way, which is always okay. We do the double or triple fermentation, so we kind of grow our yeast, then we make a pre-dough with that, and in between there's always 24 hours. We make a pre-dough, and then we put the pre-dough into the dough, and we let it ferment for another 24 hours, and then it gets shaped and gets into the oven. There's two ways how to kind of do the bread. At home you do the loaf proofing. you do like a 2 to 5 kilo dough at the best, because bigger doughs, they have better outcome. And you form a bread and you leave it in a proofing basket for 24 hours, more or less. It depends how fast your system is. And then you make a nice controlled, you toss it into a pan which is already hot in the oven, and toss it in and put it again in the oven. Keep it closed for 15 minutes, then open it and let it bake for the rest. That's the easiest way at home. I'll show you how to make a boule. What we do, we don't have space for like thousands of these. So we always make bulk fermentation. We do 15 kilos in a container, and then in the morning you pour out the dough on the table. You divide it by 500 grams, 800 grams, kilo, and you put it into also again in these, and then it stays only half an hour to 40 minutes in there until it's kind of relaxed, because we don't take the bubbles out when we move it from the table to the thing. We try to keep all the air inside, which is a secret anyway with those. I think leave it as it is, do as less as possible. I think there's always the best outcome. Give it enough time. So, yeah, I have to have a little flour. Then you can, when you do it at home and you make a loaf proofing, you proof the piece, you can have the closure down, the closure up, and then when you toss it over, you make a nice cut so the gas comes out where you want it. What we do a different way. We do the closure up, the closure down, and then when you put it in the oven, it has this wild opening, so we don't have to cut it. That's just a different system how it works. These are too light. And the dough is now kind of not in a perfect mood. I think it's waiting too long in the room temperature. So, make it a bit smaller, otherwise it doesn't. So, now you can see all the bubbles, and it's already a quite developed dough. So what you try to do is just not put any force in it. Just leave it as is, and then you can put it in the form. This is now the bread you see here. I'm not saying this is now the right moment to form the bread. It's just a show. So you see how it works, how it looks afterwards. It's really simple. You kind of don't touch it. Or there's this Chad Richardson way, the tartine way, where you fold it and make it nice and have it's almost like a ballet with your hands that you form a country loaf, which is nice. I like it. We do that too sometimes when we have fun. It just at the end, it's not that. It's not the magic. The magic is time and giving the dough its proper way to develop the way the nature wants it to be. Crucial is the temperature. If you have a cold dough and you put it in the oven, you have to put up the temperature. You have to keep it in there longer because it doesn't. The caramelization. There is no sugar on the outside. There is no caramelization. You have to wait until the Maillard reaction goes, and then you have like this big old thick crust, and the bread is not really good. So you have to have before you put it in the oven, you have to have room temperature. The best is even a bit warmer is good.
And it's actually very interesting because when I came to visit you, you mentioned about the pot that you have there, which actually is something I didn't know, right? Because so there is a big difference between the ovens that you have at your place and the ovens that we have at home, right? Mm-hmm. Which are not as good. So a way to actually overcome that is to put the bread in the pot. So how come is that?
Yeah, you have to imagine our deck ovens. They have like this 2 millimeter steel. They have like a vapor system inside where you can push the button. It goes like there's steam going into this chamber. The water that comes on the surface of the bread reacts with the sugar and the heat, and there's where the caramel is coming from. You know, with the water, there's if you put water and sugar in a pan and make it hot, you see the same effect. At home with the home ovens, it's just all the humidity. It goes right away out. There is no humidity in there. You can put like little pans in there or spray water in there. But it's like if we bake with open doors, you know, it's like it always goes like out again. So what we're trying to do with a steel or a pan like this, a cast iron pot, you try to imitate that atmosphere of moist. Of this moist air, so you get the right crust. And when you have to put it in the oven to heat up, and then you have to draw. It's a bit it's kind of a dangerous thing to burn. You have to take the hot pot out, put the bread in, slice it without having all those scars everywhere, and then put it in the oven again. You need good gloves and be fast. That's where you get this climate of that the bread and the crust needs. After 15 minutes, you take it off because then it has to dry off. It has to the caramel. If it stays wet, it doesn't work. So it has to dry off. We have like this thing, Zug, it's called in German. We open the Zug and all the vapor goes out in the back in the sky. That's what we do in our bakery. But this is a perfect way to do that at home. There's different systems. There's like stones and you just put a lid on it. There's pans and you have a lid on it. There's different ways. What we also tried once is to like just tape the doors with gaffer tape, you know, because we didn't have a pan, but that doesn't work. Because the water goes down, I don't know where it goes out there, out of these ovens. And second of all, you have to heat up really good. So I think the most of the oven goes to 230, but if you have one that goes to 250, go to 250. Fast in, fast out. It's really nice. It's really good for the bread. Depends a bit. If you have a lot of sugar or fat in there, it's a different baking. You don't want your Zopf to be as crusty as a bread, so you kind of have a totally different thing. You can do that in a normal oven because you have the egg on top. You don't want too much moisture inside the oven, otherwise your egg wash is on the paper. As I said, there's I didn't do it now, huh? I forgot to make it. There is like a funny thing to do. We discovered it a few months ago, first time. I never did it before. Because we work with Brühstück, that's where you pour hot water over the grain. We work with Kochstück, which is this one. You boil flour, water, and milk. You boil it, and it gets. Unfortunately, we were too. Normally, it is this funny pudding. This
like a panna
jello.
cotta.
Huh?
Like a panna cotta.
Yeah, like a panna cotta. And that's what we use for dough making then. And what you get is this when you divide this, you have these strings, and the crumb gets really fluffy and moist. That's what you can do if you put some Kochstück. Kochstück it's called. Put some Kochstück in there. Don't put too much in because it doesn't work. If you put more than 10% in there, it doesn't work. Huh? Yeah. What I also did, just to show, this is if you take a piece of dough. I can try to do it. You can take a piece of, take that one. And you kind of wash out the starch. You get at the end. You can wash out the gluten, which is also called. They also use for seitan, for example.
Excellent. Well, thank you very much, Jens. That was really interesting. And as I said, all the recipes are actually on the webpage. So also to make the poolish, as we said, with the times and temperatures. And also Jens very kindly scaled the recipes down to our scales, because the recipes he shared was like 11 kilos of dough. Something that you say, I mean, maybe during COVID that could have worked, but nowadays
432, and then it's like
exactly. So he scaled that down to like a 1 kilo dough, which is actually much more manageable. So there are some samplings that are going around, and with this, I would like really to conclude and thank everyone for participating. I guess we are running slightly out of time, so we don't have time for questions today, but we are still here, and so you can come down and ask Jens questions. I would just like to remind you of our next event, which is going to be on the 3rd of December with Markus Stöckle, who is a really famous chef here in Zurich, a bit of a innovative chef, and we will think about gelations, which is, we touched a little bit on today. It's another really interesting soft matter effect, and so please come to that. And then as the last thing, before I conclude, there is a survey at the exit. You can fill it down on paper, or you can also scan the QR code here. There are QR codes also at the exit. Please give us some feedback, tell us what you think. And I would like to thank, well, first Jens for really an amazing lecture.
Thank you too, Thomas. Thank you.
And also a big thank to all the people that have helped to shape this lecture, all the student helpers, all the people that are part of the Cook the Science team, and here the camera team, and the permits, and the events management. Really thank you for your help, and thank you everyone for participating. I hope you enjoyed, and I see you next time.